Thank you, William. Can you hear me?
Yes, we can hear you very well. So you can go ahead and share your slides.
Okay, that's great.
Okay. We can see the screen very well, so it's fine. It was just freezing a bit, but it looks fine.
Okay.
Yes.
Good afternoon, everyone. I'm sure you have enjoyed all the previous talks, and hopefully you will find mine useful as well. So first, please allow me to introduce my research career. I did my PhD in electrochemistry with Professor Gary Attard at Cardiff University. I used the in situ electrochemistry and surface enhanced Raman spectroscopy to study the selective hydrogenation of some ketone and alkyne molecules. And after I finished my PhD, I had two options. One was to run a lab in a newly founded research institute in China. And the other one, and this one was to use my skill sets learned from PhD and to continue the new research. And the other one was to totally challenge myself and do a completely different project. And I never regret I chose the second one, which was being a postdoc with UK Catalysis Hub. So in this project, I studied the oxy-chlorination of CO to produce phosgene. And during this project, I need to use new techniques such as infrared and use the diamond light source to run in situ XFs experiments and run the X-ray photoelectron spectroscopy tests for the samples, and even did the computational chemistry by myself. So I found it very beneficial for me to chose this project and gained a lot of more skills during my research. And now I'm at a postdoc at HarwellXPS, and I'm sure this is the most beneficial part to you today, so please stay till the end. In my PhD, I did the surface structure sensitivity study in catalytic hydrogenation at platinum single crystal electrodes. So now I'll give you one or two examples. So cyclic voltammetry is one most versatile electroanalytical technique that used to study electroactive species. It corresponds to a simultaneous measurement of current density and the versus the electron potential. And at different potential range, the hydride or oxide could be formed on the electrode surface. This is an example of the cyclic voltammogram of polycrystalline platinum in sulfuric acid. And if the potential is below zero, the hydrogen could be evolved on the electrode surface. And this is the source for the hydrogenation study. So even on the polycrystalline platinum nanoparticles, there are still many ordered facets on the surface. So we could see that different surfaces have the unique cyclic voltammograms that we use to identify them. So this is very important for the selective hydrogenation on different platinum single crystal surface. And the Raman effect or Raman scattering is the inelastic scattering of photon. So when the incident light shines on a sample, only a small amount of scattered light can make the photons move from the ground state to the virtual state, and then give us this Raman effect. And the Raman spectroscopy is a technique that used to study rotational, vibrational, and other low frequency modes. And surface enhanced Raman spectroscopy is a technique to study the absorbance interacting with the rough surface. And here we can see that a enhanced field is at this roughened surface area, and the enhancement factor could be as high as 10 to 11. And but this part, which is flatter, which gives us less enhancement. And only gold, silver, or copper are SIRS active and substrates. So now with this background knowledge, we try to design a kind of SIRS active shape controlled nanoparticles. And by the long range effect of the electromagnetic field created by the gold core, we can detect the molecules absorbed on the surfaces of platinum, and therefore make those SIRS active, and we'll be able to observe those vibrational modes of the molecules. So how do we make these nanoparticles? First, the gold solution was reduced by sodium citrate to form these kind of gold nanoparticles. Then by adding ascorbic acid and the platinum solution, we will be able to coat the 2 nanometer thin shell of platinum around the gold.
Sorry, Shaoliang.
Yeah.
I don't know if it's just my screen. The slides don't seem to be changing. Are you still on this slide?
Yeah, can you see gold platinum nanoparticles?
No. I'm still on I think it was the second slide. So, or maybe it's just my computer. I don't know.
It's the same for me. I'm on the cyclic voltammetry slide.
Oh yes, which is my slide as well. For some reason, it's the screen is freezing. I'm not sure why. Oh, I just got a message on the Q&A box as well. Apparently, a few other people are seeing the same thing. So I don't know.
Sorry, I tried to sort it out.
Oh, okay. I'm not sure if it's a settings issue or.
So do you see the screen of the self-introduction now?
Yes, yes, yes. That's the one. Yes, seems to be perfect. Okay.
And then this slide.
It changed, yeah. But this was the last. This was the last slide we saw last time. Maybe try the next one. Yeah. The next slide, yes.
That we've not seen before, so that's good.
Yes, we haven't seen this before. Yeah, it's perfect now.
Okay, yeah. Sorry about that.
Okay, sorry for the interruption. Go ahead, yeah.
No, sorry that you you were just confused that what I was talking.
Okay.
Okay, so just introduce the cyclovoltammogram of the polycrystalline platinum in sulfuric acid. And even on the polycrystalline nanoparticles, we could see the ordered surface with different unique shapes of the platinum surfaces. This is allowed to identify two different single crystal surface of platinum. And the Raman effect or Raman scattering is the inelastic scattering of Raman. When incident light shines on the sample, only a small amount of light gets scattered, and the photons travels from ground states to virtual states, give us the Raman effect. And the Raman spectroscopy is a technique to study the rotational, vibrational, and other low frequency modes. And surface enhanced Raman spectroscopy allows us to study the molecules absorbed on roughened surface, which give us the enhancement. And the key is that the surface need to be rough, and only gold, silver, and copper are surface active. So the kind of surface active shape control nanoparticles was designed so that allow us to see the molecules absorbed on platinum, which was not surface active, but by borrowing the long range effect of surface active gold core, we could see their vibrational modes of molecules absorbed on platinum. So how do we make these nanoparticles? We can make the gold platinum nanoparticles with 2 nanometers thin shell around gold. And also, if we replace the platinum shell with silica, we can make this type of nanoparticles. And later I will show how important these are. So the experiment setup was simple. The solution with the organic molecules that I was interested in was pumped and goes through the cell. And the Raman laser is shine on the working electrodes, which are decorated with these nanoparticles. So when the potential is controlled, we could evolve hydrogen on the working electrodes, therefore reduce the organic molecules that flow through the cell. So the initial selective hydrogenation of a prochiral ketone to the corresponding alcohol catalyzed by platinum was first observed by Orito in the late 1970s. And the ethyl pyruvate gives us a high reaction performance regarding the final EE, and therefore the mechanism and it's important for us to understand the mechanism of this type of reaction. So with the setup and this experiment was repeated, we could see from the black spectrum that highlight this peak, which just below 500. This is the platinum carbon bond. And this 1050 wave number is due to the platinum, the carbon oxygen, carbon OH bond close to the surface. And we could also see that some amount of CO was formed due to the high reactivity of platinum. Then a type of modifier, synchrolidine, was added to the solution. We could see that we could reduce the amount of CO formed and increase the final product yield. And this this type of intermediate is called half hydrogenated state of EP on a rough platinum surface. And this was discovered in last century. So by this point, we don't know that what kind of surface actually active for the reaction and what and this contributing to the CO formation. So before I started my PhD, the type of shell isolated nanoparticles enhanced Raman spectroscopy was designed, or shiners it's called. This kind of shiners nanoparticles were made of gold core and silica shell. And because silica is electrochemically inert, so it doesn't affect the electrode that it's deposited on. So by replacing these gold platinum nanoparticles with gold silica nanoparticles, we'll be able to study the molecules interact with platinum single crystal surface, and it can boost the intensity of Raman scattering from molecules absorbed on flat surfaces. So this is the groundbreak. Then again, I studied the EP hydrogenation on different platinum single crystal electrodes. First, let's look at the platinum 111 surface. And this cyclophotomegram shows that after depositing the nanoparticles on it, it remains in its features, which prove that this nanoparticle is inert. Then again, with the same experiment setup, we look at the black spectrum and achieved. So different from the previous spectrum, we could see that just below 500 wave number, that peak was disappeared. Then instead, a sharp peak appeared at 420. And the 1050 wave number peak also disappeared. And instead, a peak below 1000 was observed. And this, we found that it was the precursor of the half hydrogenated state absorbed on the platinum terraces, and because of the ordered platinum 101 surface. And then if the surface was electrochemically roughened, and we could see that the peak below 500 and the 1050 wave numbers reappeared. That means the EP half hydrogenated state reappeared together with the CO formation. And then the previous two peaks attenuated. So the half hydrogenated state requires a defect size of on the platinum surface. And again, by adding CD, we could reduce the CO formation and increase the yield of the product. So how about platinum 100? And similar results from the platinum 101, because it's a very close compact ordered atoms on the surface. We didn't see the half hydrogenated state. Instead, we saw the precursor. And then when it's roughened, we saw both states appeared on the surface. And what do you think of 110? Well, because 110 surface is quite different from the previous two, and even on a very clean surface, it could be the rows could be there could be missing rows on the surface and causing the defect sites. Therefore, both half hydrogenated states and precursor appear on 110 surface. And this is to conclude, and that EP half hydrogenated states happens on the steps, and the new intermediate was found adsorbed on terraces, and CO can only be generated on defect sites. So we know what kind of surface we need to avoid CO formation, and the CO production can be reduced by adding the modifier, centrality. Okay, now I'll move on to my postdoc research project with UK Catalysis Hub. It was the Phosgene formation by CO oxy-chlorination. And in industry, the isocyanate manufacturing is via Phosgene. And the Phosgene was made by passing the CO and the dichlorine through activated carbon. Then the Phosgene reacts with amines to form isocyanate. It is a very important reaction for polyurethane manufacturing. And my project was, however, during this process, a large waste of HCl was formed and cannot be recycled. And my project was to use copper chloride catalyst to react and to make CO react with this HCl and oxygen to form phosgene. So this is a very great challenge for the environmental theme. So we always found that the project doesn't go well from the beginning, and so was mine. And by increasing the temperature of the CO and the gas flow of CO and HCl, we could see that at the reaction temperature, actually only carbon dioxide was formed. So it tells us that the catalyst doesn't work. So what should I do then? And because the CO oxy-chlorination, we requires the phosgene, we requires the chlorine as a resource. Then by pre-treat the catalyst with small amount of dichlorine, we can activate the catalyst. And then when the mixed gas flow of CO and HCl pass through the catalyst, we could see that besides CO2 formation, which was attenuated, we could see the phosgene formation finally. But there's another issue, which is we could see that although the more dichlorine we used to treat the catalyst, the more phosgene we could produce. Like the picture shown on the left, and the red one had more treatments of dichlorine, and we had more phosgene formation. And meanwhile, the CO2 formation was reduced in this different treatments. But we could see that the reaction, the product decrease with the time. So that means the catalyst was deactivated during the process. We all know that the catalyst is a surface reaction, so it must have something to do with the active species of copper catalyst on the surface. So the X-ray photoelectron spectroscopy, which is a surface technique, was used to study the catalyst change. We could see that during the increase of the temperature till the working temperature, the copper 2+ active species remain on the surface. And only after the catalyst react with CO at this temperature, after half an hour to 1 hour, the active species disappeared. Instead, it's the reduced copper 1+ species on the surface. So this proves that the catalyst surface was deactivated during the reaction. So this brought me to the most important part for you guys, which is the HarwellXPS that I'm working at now. It is a national facility for the surface analysis, and we have the several branches which contain state-of-art XPS spectrometers. In research complex at Harwell, we have 2 instruments recently upgraded with Raman as well. And in Manchester, we could do near ambient pressure XPS. In Cardiff, we have a catalysis high pressure cell. And at UCL, we could do angle resolved XPS. And the team has Professor Phil Davis from Cardiff, Rob Palgrave from UCL, Dave Morgan from Cardiff, and Wendy Flevel from Manchester. And Dr. Mark Isaacs and me are working at the research complex at Harwell, and together with Dr. Alex Wharton from Manchester Hub. So in case you're not familiar with where we are, here are the cities, and we are based at south of Oxford, near the Diamond light source. And not only we provide the data sample tests and the data analysis, we also do a lot of trainings for people with different backgrounds. And also we participate in a lot of events too. So XPS looks simple, but to avoid mistakes, you must get trained by experts. We received thousands of samples, and you can see that the catalysis is occupies the most part among those samples. And we have a network of more than 200 principal investigators and then many more postdocs and students who used our service. So in order for you to know if it's beneficial for you, in the last part of the talk, I will give you a brief introduction of the fundamentals of XPS. So we all know this man, Albert Einstein, but not all of us know that he received the Nobel Prize in Physics for explaining the photoelectric effect in 1921. And Kai Seeban uses his ultra-high vacuum spectrometer to observe photoelectrons generated by X-ray, and he also received the Nobel Prize in 1981. And at that time, he called this technique Electron Spectroscopy for Chemical Analysis, or ESCA, which is equivalent to XPS. So XPS instruments may look different, but the principle is the same. When the X-ray source irradiates a sample, it can penetrate microns depths of the sample, but only the top 10 nanometers of the photoelectrons could be able to escape from the surface without losing the energy. And these electrons will be collected by the analyzer. And if we look closer at the surface, when the X-rays shine on an atom, and all the electrons will get energy and may escape. Only the core electrons, which are characteristic to the element, will carry the information of what the element is. And these photoelectrons will be collected and then used to identify the element. And if we look at those electrons in the core orbital, after they escape from the atoms, and they have certain kinetic energies. And with this equation, we know the kinetic energies of the photoelectrons and the X-ray source energy, and we'll be able to calculate the binding energy of the photoelectrons, therefore to identify the elements. So why is it a surface technique? Because the X-rays is a low energy, and so the photoelectrons are relatively slow. Therefore, during travel, most of them will hit other atoms that generate hit other atoms in the sample and lose energy. So only a few electrons can get out unscattered, which gives us the photoelectron peaks in the spectrum. And many more get out of the surface but have lost energy, which make up the scattered background. What can XPS do? And we can study the surface of solid metals, powders, and even liquids nowadays with the cryo-frozen technique. And it is a quantitative method. Therefore, it allows us to identify the chemical composition and their oxidation states quantitatively. And with the ion etching, we will be able to do the depth profiling for solid materials nowadays in order to study the bulk of the samples. So a typical feature of a photoemission spectrum, and this is a wide scan of XPS spectrum. We could see that there are peaks originating from oxygen 1s orbital at 533 binding energy, and carbon below 300. And we can also see that there are several peaks originated from silver, such as silver 3D, 3P, and 3S peaks. And these are core lines of the spectrum. And by studying core lines, and we need to know the chemical shift or peak position, and their shape and width, and intensity, and the spin orbit coupling. Therefore, we'll be able to confirm the chemical composition of a whole compound. So chemical shift is a simple model, which is the charge or chemical environment of an atom causes small changes in the binding energy of its core lines. So this allows us to identify the chemical environment of an element. For example, in this table, we could see that tungsten 4+ is more oxidized, therefore it has higher binding energy than tungsten metal. And the 6+ has higher binding energy than 4+. And with different ligands, because fluorine is more electrophilic, and it has the tungsten has higher binding energy than this tungsten trioxides. And once we know where the peaks should be, and we will need to identify the peak width and shape. And the peaks is a convolution of energy spread of X-rays and the spectrometer broadening and the intrinsic line width, which is due to the lifetime of the photoelectrons. And the first two are Gaussian shape. And the last one is a Lorentzian shape. And the total full width at half maximum, which is this part, is used to identify the peak width and shape. And next is the peak intensity. So intensity of core-line peak is made of with this equation. J is the X-ray flux, C is the concentration of the element, sigma is the photoionization cross-section, which is used to define how easy the photoelectron can come out. And zeta is the spectrometer angular acceptance, and T spectrometer transmission function, and lambda inelastic mean free path of the photoelectron. So it looks complicated, but all the yellow ones this should be the spectrometer constant, which is fixed for certain instruments. And this one is also assumed constant. So actually the intensity of core-line peak is decided by the concentration of the element and the photoionization cross-section. So by identifying the intensity of the peak, we'll be able to see the concentration of the element of interest. And not all the peaks are as simple as sodium 1s peak, which is just one peak. And there could be spin orbit coupling. For example, this gold 4f has a doublets, and the doublets have a certain relationship between them. So the coupling happens when the electron spin and the orbital angular momentum, and when the orbits are, when the L is greater than 0. For example, for the PDF orbitals, the L are 1, 2, and 3. And the S means the electron spin, which could be up and down, which is plus half or minus half. So the coupling J is equals L plus or minus half, give us these J values. The spin orbit doublets are characterized by splitting energy constant, intensity ratio, and the full width at half maximum ratio. For example, the gold 4F, we saw that they always appear as a doublets, and the certain distance never change. And the ratio between these two is 3:4. And the full width at half maximum always the same. Only a small probability for some elements, these two peaks could have different shapes. And this silica 2p looks like a single peak, but actually because the splitting energy constant is very small, and it's just below 1 eV. So therefore, we should always remember that there are actually two peaks with 1:2 ratio, which consists of these silica 2p peaks. So all the above was about the primary structure of the photo emission spectrum. There are also secondary structures. For example, the asymmetric, the shake-up feature of the HOPG, which is a conductive metals. But that for diamond, there's no such peak here. And the plasmon lines happen to the metal samples when the photoelectrons interact with the electrons in the valence bands. And sometimes the peaks could be, there could be many more peaks under the one element, and make it multiple splitting. which this is due to the unpaired electrons in d orbital of iron. And these asymmetric peaks observed on the aluminum metal surface. However, the native oxides, we could see that they are symmetrical. So all of this is to just give you a taste of what the XPS is, and you may find that in your study it will be beneficial for you to run the sample tests of the using XPS. So, due to the time limit, today I can only introduce this much. And please visit us at this website. You could apply for an XPS test with us and follow us. We have channels, YouTube channels, and a lot of recorded lectures for you, and a lot of resources at this website. And finally, this is the acknowledgement. And thank you much. Thank you very much for your listening.
Thank you very much, Shaoliang, for such a detailed presentation on XPS. Please feel free to add your questions on the Q&A box. I'll read them as they come up. I'm just checking here on, maybe just a quick one from me, Shaoliang, while people are typing their questions.
Yeah.
On the Phosgene experiments, it was interesting to see that some copper species is active and then the other one doesn't seem to be so active. Did you just run, I'm wondering if it was just the CO reducing the copper, because CO is a reducing gas. Did you run TPR, say maybe under hydrogen or CO, just to observe the reducibility of the catalyst? Are these copper nanoparticles, the copper chloride? Is it nanoparticles? Yes. Or?
Yeah, they are
nanoparticles. Ah, okay.
Yeah, actually, yeah, they are industrial catalyst used for decom processed, and we use to grind it to nanoparticles and make this kind of small scale reactions.
Oh, okay.
Yes, and it's a copper chloride and the potassium chloride mixed catalyst, and it seems that because it is supported on a kind of clay, which is called palgite, which consists a lot of hydroxide groups. We assume that the CO2 formation was due to the reaction of CO with the oxygen resource from the support and give us the byproduct CO2. But after treating it with chlorides, we can suppress the support effect, and CO can reach the chlorine source and give us the phosgene formation.
Oh, okay. Thank you very much for that. I think people, I mean, I don't see any questions on the Q&A box. I think people are already looking forward to the short break. So, yeah.
Yeah, no problem. But I'm sure later they will find me, look for me for the XPS test, and it's more than welcome.
Of course, yes. Thank you very much. Thank you very much.